Okay, let's start. Today it's our honor to have Jason Peng to have a talk at our group meeting. Jason is an assistant professor in the School of Computing Science at SFU and a part-time research scientist at NVIDIA. He received a PhD at UC Berkeley and an MSc and BSc at UBC. His work leverages machine learning to develop motor control models that enable simulated agents and real-world robots to reproduce the agile and versatile motor skills exhibited by humans and other animals. He has received an outstanding doctoral dissertation award from ACM SIGGRAPH and an early career research award from Graphics Interface. Now I'll pass the time to Jason.
Okay. Yeah, thanks, Tianyan, for the introduction and for inviting me to speak here today. I'm going to be sharing some of the work that we've been doing on building controllers that enable humanoid agents to reproduce versatile and lifelike behaviors. In the past few years, we've seen very rapid progress on humanoid robotics, with new demos coming out on almost a weekly basis, showcasing humanoid robots performing some incredibly agile and lifelike motor skills. There's a lot of sophisticated engineering that go into making these systems possible. But one of the common recipes that underlie many of these impressive results is the use of reinforcement learning and motion tracking. This combination of RL and motion tracking has proven to be a very general recipe for building controllers that can reproduce a wide range of motor skills. And so in today's talk, I'm going to go over a quick review of how these RL-based motion tracking techniques work, what are some of the limitations, and how we may be able to go beyond motion tracking in order to develop more versatile and useful controllers. To start, let's say we have a humanoid agent, and we want this agent to be able to move in a natural and human-like manner. The most effective method that we have for doing this currently is by using some form of imitation learning, where we record a demonstration from a human actor, often in the form of a reference motion, and we then construct a controller that reproduces that behavior by mimicking that reference motion. Now, to create such a controller, more and more frameworks nowadays will use some form of reinforcement learning, where we have an agent that interacts with an environment in order to perform a particular task. At each time step, the agent is going to observe the state of the environment, and it would then select an action that it should take in order to influence the environment in some way. This action will then lead to a change in the state of the environment, and the agent will in turn receive a reward that tells it how good that action was in the context of a given task. The goal of reinforcement learning then is to try to learn a policy, often in the form of a neural network, which will select the appropriate actions that allows the agent to maximize the cumulative reward that it receives from its environment. Oh, also, if anyone has any questions over the course of the talk, don't be afraid to interrupt. Okay, now for a lot of these motion tracking problems, we'll often model the policy as a tracking controller that takes as input the state of our agent, as well as a sequence of target states from the reference motion that we would like the agent to imitate. The policy would then output motor commands, things like torques or PD targets, that will be applied to drive the movement of the agent's body. Now, the key to training a controller to do what we want lies in how we design the reward function. And for most of these motion tracking frameworks, we will use a fairly straightforward tracking and reward function that simply tries to minimize the difference between the motions that we see from the reference motion and the motion that we observe from our agent. So given the reference motion, the reference motion will specify target states that the agent should be in at every time step. And the job of the policy is to select the appropriate sequence of actions that will allow the agent to track that sequence of target states as closely as possible. The reward in this case can simply be computed by taking the difference between the target state from the reference motion and the state of our agent at each time step. In some of our earlier work with Deep Mimic, we showed that this combination of reinforcement learning and motion tracking provides us with a very general framework that can reproduce a wide range of motor skills. While these motion tracking methods can be effective for a diverse set of skills, they do have some major limitations. One of these limitations is that the tracking controller that we get at the end of this process is not very flexible. These tracking controllers are more or less stuck just playing back the same motions over and over again, and they can't really do much else. And in a way, you can think of these tracking controllers as fancy wind-up toys. You wind them up and you set them loose, and they just play back the same motions over and over again. Now, this is great for creating fancy demos that can showcase what our humanoid robots can do. But if we want our agents to perform more useful tasks in the real world, then chances are motion tracking alone will probably be a little bit too restrictive. For example, let's say we have a fairly simple task where we have our agent and we want this agent to go and punch an object. If we want to apply motion tracking to this particular task, we'll first have to go and record a reference motion that shows how the agent can walk to the target and punch it. If we have a suitable reference motion like this, then we can just simply apply motion tracking to train a controller to perform this particular task. But now if we change the task a little bit, like let's say we move the target to a slightly different location, then this reference motion may no longer be suitable for this slightly different variation of a task. And in this case, we might have to go and record a different reference motion for performing this slightly different instance of the task. Now, this won't be a problem if we have tons of motion data that gives us a good coverage of all of the different variations of a task that we may be interested in. But unfortunately, for a lot of motion control problems, we are often working in a very data scarce regime where we may only have a few sparse examples of how to perform certain variations of a task, but we want to train much more versatile controllers that can fill in the gaps and be able to perform all variations of a task. In addition to performing all these different variations of a task, we will ideally also like our controllers to be able to produce very natural and lifelike behaviors. And this is particularly important for applications in computer graphics and robotics. Okay, so how can we go about training these more versatile controllers? One way that we can go about this is to take the original motion tracking objective that we started with and replace that with a more general distribution matching objective, where instead of training a controller to exactly track a reference motion frame by frame, we'll instead simply try to train the controller to match the behavioral distribution that we observed in our motion data. One way that we can implement such a distribution matching objective is by using adversarial imitation learning, where we model the imitation objective using an adversarial discriminator that's trained to predict if a given input motion is from the motion dataset or was a motion produced by our agent. And our controller would then be trained to try to produce motions that fool the discriminator into thinking that they're motions from the original dataset. So this is more or less the same setup that you have for any GAN framework. But now by using this adversarial imitation learning objective, you can then construct a more flexible method for training our controllers. So in this work, we're going to train our controllers using an objective that consists of two components. First, we have a task objective, which encourages the agent to perform certain high-level task objectives, like moving to a target location or hitting an object. And then the second component will be a style objective modeled using our adversarial discriminator, which encourages the agent to try to perform that task while using fairly natural and lifelike behaviors similar to those that we observed in our motion dataset. By using an objective that decomposes task from style, we can use the task objective to encourage the agent to perform all variations of the task, while we can use the style objective to try to ensure that the agent is able to perform those new tasks using fairly natural and lifelike behaviors. So this is the setup that we are going to be working with, and let's see what we can do with this approach. Here we have an example of a data set that contains a mix of different punching and locomotion behaviors. We can train a discriminator with using this data set, and this then allows us to train a fairly versatile controller that can walk to different targets and punch them. So the key thing to notice in this example is that our dataset doesn't contain any examples of this task. So we don't have any motion data of a character walking to a target and punching that target. But by training a policy with this adversarial discriminator, we provide a policy with the flexibility to combine and compose different behaviors in the dataset together in order to perform this new task, which we didn't have any data for originally. And we certainly didn't have any motion clips of a character walking to and punching any of these specific targets. Here's a different task where we train a controller to dribble a soccer ball to a target location using a dataset of different locomotion behaviors. And again, here our dataset doesn't contain any examples of a character dribbling a soccer ball, but our model was able to repurpose and adapt the locomotion behaviors in order to perform this new task. Now, another fun thing we can do with this adversarial method is that we can train controllers to automatically recover from large perturbations. So here we have a dataset of different locomotion and get-up behaviors. And by training a controller with this dataset, we get a controller that can automatically transition between different locomotion and get-up behaviors automatically. So when the character falls down, it automatically learns to execute a get-up behavior in order to get back up and then transition back to a running behavior. And the composition sequencing of these different skills emerges automatically from the training process. We don't need a high-level planner to tell the character when to run or when to get up. The compositions just emerges automatically from this adversarial objective. These more versatile imitation learning objectives become more and more important as we try to train controllers for more complex tasks, where it might be very difficult to collect a sufficiently large amount of motion data to cover all the different types of interactions that our agent might need to perform. So in this examples here, we have trained a controller to interact with different objects in the scene. And for these types of scene interaction tasks, it's going to be very expensive to try and collect enough motion data that gives us a good coverage of all the different types of objects and interactions an agent might have to perform with these different objects. But with adversarial imitation learning, we can start with a fairly small motion data set that only contains a few examples of how a human may interact with different objects. And with this, we can then train a much more versatile controller that can interact with these objects, starting from lots of different initial configurations. So here we have a controller that was trained to walk to a chair and sit on that chair, starting from lots of different initial positions. And many of these initial positions are well beyond what we had in the original training data. And this same controller can also be applied to walk to and sit on lots of different pieces of furniture, things like chairs, stools, and couches. And again, many of these objects were objects that were not in the original training dataset. But the adversarial learning process provides the agent with the flexibility to adapt the existing motions to these new objects. Here we have a different pick and place task where a character has to go and pick up an object and move it to a target location. And again, with our method, the controller is able to move objects starting from lots of different locations, as well as objects of different sizes and masses that goes well beyond what we had in the original motion dataset. So one way that we can go about training more versatile controllers is by using more flexible imitation learning objectives. But another way that we can go about training more versatile controllers is to simply use more motion data. So if a lot of the challenges that we have in motion control stems from scarcity of motion data, then if we simply make our motion data set bigger, then maybe a lot of these problems will go away. But as we mentioned before, acquiring a large amount of motion data can be fairly expensive for a lot of different applications. So simply trying to record our way out of this problem might not be very scalable in the long run. So a potentially more economical approach is to leverage synthetic data, where we can take a small motion data set that we started with initially, and then augment that data set with synthetic data to try and fill in the gaps and provide better coverage of all the different scenarios that our agent might find itself in. One way that we can go about generating synthetic data is to leverage all the great work that has been done for generative modeling, where we can take our initial motion data set and we can train a generative model on that data set. And we can then use that generative model to generate new synthetic data that we can use to augment our data set. So you can pick your favorite generative model here. You can pick a VAE, again, a diffusion model, take your pick. But once we have generated a large amount of synthetic data, we can then use that data to train a controller. And this will hopefully allow a controller to acquire more versatile behaviors that can provide better coverage of all the different variations of the task that we might be interested in. So for example, let's say we have a fairly simple locomotion task where we have a simulated character and we want this character to move to some target location. In this case, we can train a motion generation model that we can use to generate lots of locomotion behaviors that show how the character can walk to different target locations. So if we can generate a reference motion for performing this particular task, then we can just apply good old motion tracking to train a controller to move to that target location by imitating the specific reference motion. And in this setting, the generative model is effectively acting like a motion planner that generates reference trajectories for the character to perform different variations of a task. So here's kind of one example of this framework in action. Here we've trained a text condition motion diffusion model, which can generate a large amount of motions given a particular text prompt, like jogging, jumping, or dancing. So by conditioning the diffusion model on a particular text prompt, we can use it to generate a large amount of data of that specific behavior. And then we can use that data to train a controller to move to a target using these different stylistic behaviors. Here's a slightly different variation of the task where we condition the model on different prompts like pushing, kicking, and punching. And we can generate a large amount of data that allows us to train a controller to hit an object in different ways. Now, admittedly, these are fairly simple tasks, but a similar approach can also be applied to a more complex domain as well. So here we have an example of some motion data that we reconstructed from videos of professional tennis players. With this motion data, we can train a generative model, in this case a VAE, that can then be used to generate a large amount of tennis playing motions. So given this generative model, we can then train a low-level tracking controller to imitate the behaviors from the VAE, and this then allows us to train a simulated character to play a bit of tennis. So here the simulated character was trained to hit incoming tennis balls back to a variety of different locations on the opponent's side of the court. And it's able to do a pretty good job for the most part. So if we have an effective generative model, we can use that to generate a large amount of motion data for training more versatile controllers. But there's a limit to how far we can push these generative models. Because these generative models are typically trained using a relatively small amount of motion data, they can have trouble generalizing to new scenarios that are very different from what we observed in the original dataset. In this example, we trained the diffusion model to generate motions for traversing across irregular environments. And in this particular case, the terrain that the character is running on is quite different from those in the original dataset. So this generative model ends up struggling to generalize to this new scenario, and it ends up producing very unrealistic behaviors where the character is just floating around everywhere. So trying to train a controller on these particular motions may not lead to particularly good results. So in a sense, if we want to train a versatile controller, we also need a more effective and versatile motion generator. So one idea that we will have here is, if we are already using synthetic data to train our controllers, why not also use synthetic data to train our motion generator? So let's say if we take our initial data set and we train a motion generator on that data, we can use that data, we can use the generator to generate a large amount of synthetic data that can then be used to train our controller. But once we have trained our controller, we can record new motions from our controller, and then we can feed those motions back as additional training data for our generative model. And we might apply some additional filtering to remove any motions with egregious artifacts. So by recording motions from a physics simulation and using that as additional data for training our generative model, we can take some of the physically implausible behaviors that was produced by the generative model, and we can fix those artifacts using our simulation. And these physically corrected motions can then be used as additional training data to train the motion generation model to produce more physically plausible behaviors in these new environments. And this then leads us to an iterative data augmentation framework, where the generative model can be used to generate motion data for training our controller, and our controller can in turn generate more data to improve the capabilities of our motion generation model. And we can repeat this loop iteratively to progressively expand the amount of motion data that we have for training our model, and iteratively improve the performance of both the motion generator and our motion controller. So this is the idea for our framework, and let's take a look at what we can do with this. So here's the initial motion dataset that we started with, which contains only 14 minutes of different locomotion behaviors for traversing across different environmental obstacles. Now, given the small motion dataset, we can train a motion diffusion model so that given a new piece of terrain, we can first generate a random path through this environment by using, let's say, an A-star planner. Given this target path, we can run our motion generator along this target path in order to produce a reference motion for traversing this environment. Once we have the reference motion, we can then train a physics-based tracker to imitate that reference motion in order to traverse across the environmental obstacles. And we can then record the motion from the simulation back and add that as additional training data for our motion generator. And if we analyze the performance of the motion generator at different iterations of this framework, we can see some pretty noticeable improvements over time. So at the first iteration, when the motion generator was only trained using the initial motion dataset, uh, the model can have trouble following the target path. So in this case, the character is prone to just getting stuck near the beginning of the path and is not really able to make much progress. After one iteration of this framework, we get a more effective motion generator that is able to better follow the target path, but the generated motions can still produce some visible artifacts. And after a couple more iterations of this framework, we get a more effective motion generator that's able to follow a target path while still producing more physically plausible behaviors. And by applying this iterative framework over and over again, we can take the initial 14 minutes of motion data that we started with and expand that to over 900 minutes of motion data. And this then allows us to train a much more versatile controller that can traverse across some fairly complex environments. In this video, the green character represents the kinematic reference motion that's produced by our motion generator. And the blue character is the physically simulated character that was trained to imitate the reference motion in order to traverse across these irregular environments. And in this case, the simulated character is able to do a pretty good job at clearing some of these very complex environmental obstacles. And at the end of this, we then get a fairly capable controller that can traverse through some fairly complex randomly generated environments. So for the most part, the character is able to do a pretty consistent job clearing these different environmental obstacles, but it's still prone to making some mistakes every now and then. If we analyze, we can also analyze the behavior of the physics-based controller at different iterations of this framework, and we can see some pretty interesting emergent behaviors. In this example, the character discovers a motion for jumping across a large gap, catching itself on the opposing ledge before climbing back up over the ledge. And this was a motion that we did not have in the original dataset. But our framework was able to discover this new behavior for clearing a challenging obstacle. Here's another example of a new behavior that was discovered by the controller, where the character learns to jump down from a tall ledge, catch itself on a lower ledge before jumping down to the ground. And this is an example of a behavior that can be quite dangerous to try and record from a human actor. But our framework was able to compose the behaviors in the dataset together in order to create this new strategy. Okay. So we've discussed two approaches that we can use to try to train more versatile controllers given limited datasets. We can use more flexible objectives like adversarial imitation learning, or we can try to expand our dataset by making use of generative models and synthetic data. Now, most of the results I've shown so far has been primarily from in simulation. But we are also working actively to try to deploy the controllers that we have trained in simulation to robots in the real world. So here we have an example of a motion tracking controller that was trained on a decently sized dataset that was then deployed on a real G1 robot. And it then allows the robot to perform some fairly agile behaviors. Though with the pace that things have been going at, I think in the more recent results, we've seen even more agile and dynamic behaviors. But that being said, these control doesn't work all the time. And in fact, the robot is still prone to falling as often as not. But these tracking controllers are improving very quickly. And my hope is that as these tracking controllers improve, they can provide a versatile library of low-level skills that can then act as a foundation for building much more capable and general-purpose humanoid robots. Okay, yep. Yeah, so that's mainly everything that I wanted to cover in this talk. I just want to take a moment to thank all of my collaborators and students I've worked with over the years. With all their hard work, none of this work would have been possible. And I'll wrap things up here, and I'll be happy to take any questions that folks may have.
Yeah, I have a question.
Yep, go for it.
So, this is more of a practical question. When you're
Mhm.
training humanoid robots and deploying them in real life, what are some things that you need to watch out for, or things humanoid robots have demonstrated in real life that you didn't expect to happen?
So I think the biggest thing is always kind of the sim to real gap. So when deploying things on the real robot, I think we always run into large discrepancies in the motor and also challenges with latency. So I think anything you can do to do proper system ID to reduce the sim to real gap, that would just make deployment all the easier. So unfortunately, I don't think there's like one secret ingredient to deploying things on the real robot. There's a lot of little details to get right, and those are kind of some engineering challenges that you have to deal with.
When dealing with dynamics differences between
Mhm.
them and real, is it usually just using heuristics, or do you have a perhaps more formal approach to gapping that?
It's mainly, unfortunately, it's also mainly heuristics. I don't think we necessarily have principal methods that says that if you do this, you'll be able to bridge the sim to real gap. It's a lot of domain randomization and looking at what the differences are in the behavior of this real robot compared to simulation, and trying to adjust your simulation or your randomization scheme to try to account for those discrepancies. So unfortunately, it's more of a craft than a science, I think.
Thank you.
I have a question.
Yep.
First of all, nice talk. I really like this visual humans. So my question is, I saw a lot of tasks that involve like a single human doing things in solo.
Yep.
Um, I wonder, like, is it like how hard it is, or what do you think it would take to make like simulate collaborative tasks such as like two human crossing each other in a
Yep.
sidewalk, or one human hand over an object to another.
Yep. Yeah, so I think the main challenge is just lack of motion data. Most of the motion data sets that we currently work with, they only show a single actor at a time. There's starting to be some motion data sets that show interactions between multiple characters, but they're still much smaller in comparison. And from my perspective, the same methods that we apply to a single character can also be applied to multiple characters as well. For the most part, you can treat multiple characters as just one big character. So once those data sets become more available, I think we should very well be able to train controllers for multi-agent interactions.
Right, I see. So, what data source do you usually use?
We mainly work with AMAS and the file.
Is that like captured by yourself, or it's like you like online videos?
On the public motion capture data sets.
I see.
Yep.
Okay, thanks.
Mm.
Uh, I also have a question about the work.
Yep.
Yeah, first of all, yeah, thank you for the nice presentation. And actually, we could see there are so many actually the simulation and Europa gap in the latest humanoid work or quadruped work, right?
Mhm.
And but I could see in your presentation there's some like really fantastic like the retargeting and also happen in simulation, motion to simulation, right? But
Mhm.
the reason for using simulation actually is actually physically grounded, but still we can see the gap between the simulation and real world.
Yep.
So I want to know like the what is actually focused on the like the your simulation you're using. For example, in simulation also designed for like the purpose. For example, like but in reality, we have like the hard actuation limitation. For example, joint limit and also torque limit or something, and also like robot dynamics not fully considered. But simulation we can actually abstract that way. That can be the reason why simulation actually work better and then actually.
Oh, sorry, I think you're cutting off a bit.
I want to
No.
know like what what
Oh,
actually have you focused in.
oh, sorry. I think you're cutting off.
Oh, okay, sorry. Yeah, maybe
Sorry,
then.
what's the question?
Okay, so in your work in simulation what you have focused I want to know what you have focused on, like for example, like do you want to try the like, have you considered robot dynamics I mean not robot dynamics I mean dynamics, or also have you considered any like actuation limitation or tra- or those kind of like the transition, have you considered transition model for actually moving the agent to do work?
Oh, so the question is like what things we model in simulation?
So simulation, I mean, in simulation, of course, we can actually consider all the actuation as well, right? The actuation limitation, but
Yeah.
if we can provide like the unlimited the torque input can
Yeah.
be given to robot, right? So, but it may not be like happen in real world, but in simulation we
Yep.
can consider that. But that
Yep.
actually makes the reason why deploying the robot, I mean, deploying the policy in the robot will be more challenging, right?
Right.
So just want to know, like, I mean, how much actually when you work on this kind of.
Right. Yeah. So generally we do impose torque limits in simulation, and we also have a joint limits as well for all of these characters.
Mhm.
But that being said, s- s- so it, part of it depends on what the simulation supports. In this particular work, we were using Isaac Gym, which
Mhm.
unfortunately doesn't support torque limits for spherical joints. So our character in this particular work doesn't have torque limits. But for some of the other work where we are deploying things on the real robot, we are modeling torque limits and also joint limits for the robot in simulation. So that does help to bridge the sim to real gap, but again, it doesn't quite get you all the way there.
So then you're not actually focusing on the more like the sim to real gap, but you're focusing more on the like the motor skills or transfer. Just
Um,
curious.
so it
A high
depends on the
level,
project. So for
in high
projects that are
level.
focusing primarily in simulation, yes, we don't focus as much on making sure that the simulation is realistic. We just try to focus on trying to do interesting skills. But for some of the work where we do try to transfer things to the real robot, we try to be a bit more careful in how we model things in simulation. Yeah, so it depends on the project.
Okay, okay. I see. Thank you.
Mhm.
Hi, I have a question.
Yep.
Yeah, thanks for the talk. I personally work in the humanoids field, and I feel like basically we take so many efforts on finding like the good resource of the like retargeting the motion because that's always the starting point. So
Yeah.
I'm wondering like for you like latest work which is PARC, like do you consider a mechanism of like filtering out some like bad quality motion for the generator, or you just like keep expanding like the 14 minutes demo to 900 demos, 900
Right. Right. So in this particular framework, we sorry, one sec. Right. Oh, right. So for Park, maybe one of the understated steps in the system is the filtering that we apply to the motion data to try to remove any data, to try to remove motion synthetic data that has egregious artifacts. So when you generate motions from the simulator and you record motions from the simulation, it's very possible that there will be quite a bit of artifacts. So you might see a lot of jittering or penetration. And so we have some heuristics to try to filter out those motions. The heuristics are far from perfect. So some of the synthetic data that we add back does still contain those artifacts. And as a result, if you look at the final results from Park, you do still see very visible artifacts in the motions that are lower quality than what we have in the original data set. So unfortunately, if you repeat this framework many times, we do expect the motion quality will degrade. But one interesting direction for the future would be to develop maybe better heuristics or better filtering techniques that can allow us to remove some of those bad motions that we don't want to keep.
So the filtering is meaning like you have a batch of like candidates data you want to track, and then you give a score to those data based on like whether those motion are visible enough to make the same like policy to go from starting to ending point.
Yeah.
And
Yeah.
then,
So that's one of the criteria. We also have criteria like detecting large jerks in the motion discontinuities, and also any penetration between the character and its environment.
I see. But how you balance like when the policy is already like well trained, so like any shaking is not caused by the policy itself, it's just caused by like the low quality of the like reference data.
Right. So if you have a low quality motion, the controller will produce low quality results, and we just filter those out. So we don't add those motions back to the data set.
Yeah, sure. But I'm saying like how you confirm like those like low quality data in the simulator, in the physics-based simulator is not caused by the policy itself, it's not well trained. It's
Oh, I see. So when training the controller on the motion data, I think we just set on a certain number of we just set a budget of a total number of samples that we will train the controller for, and then we just stop after that.
okay, I see.
Yeah. So it's possible that maybe for some very challenging motions, maybe the policy didn't quite have enough time to learn that motion well yet.
Okay, but you still have a like fair comparison between like different like candidates of the reference motion. So you always filtering out which reference motion is more promising.
Yeah. So we'll train on all of the motions for roughly a similar amount of samples.
Okay, cool. And in the future, I feel like so many different groups may have some work on like encoding those like huge set of like reference motion to a latent space, and then directly using the latent space to control as the new interface to control like the physics-based policy. Do you think that is a like interesting method or interesting direction?
Yeah, I think it's a promising direction. We had a bunch of papers that does exactly that.
I see. So from your opinion, like what's the most benefit from using like the latent space instead of like add additional like decoder to generate like the to decode like the motion and then back to the original like tracking interface. So
Yeah, so the main benefit is that you don't have to rely on a motion planner to generate your target motion anymore. So with a latent variable model, you're effectively learning the communication interface between your high-level planner and your low-level tracker. So I think that might be a bit more flexible than forcing your low-level controller to always just follow a target reference motion.
I see. Okay. But you are saying like probably we need to use end-to-end training to enable those like communication mechanism, right? If we just like, always first train like the encoder and then we don't have those ability.
Yeah, that's right. So in our previous work that trains these latent variable models, we always just train the whole model end to end. So you learn that latent representation alongside the policy.
I see. Okay. And I have one more question. It's like I know some of the teams like they want to build like the generative model part, train on as much possible as they can. For example, the reference motion may have some minor collision. For example, the two formal arm are like crossing each other, and the arguing like at least they want the like generator be aware of those data, and then somehow in the future they can generalize to more case. I don't know like why they have this argument, but I basically my personal view is like in the opposite way. I feel like if they want to like train the generator even without like your framework, we first like rule out we first like do the like very strictly remove some like invisible motions, and then we only train on a small set of the data of the like source high quality data set. But the argument is like they always train with like as much as possible, as long as like they found the same like retargeter, the retargeter have some decent like decent behavior, but they just don't remove like the outlier. So I'm not quite sure like what's your opinion on those two like two ways. Is like one is remove as much motions as you can to make sure you always start from a small but clean data set. Another direction is like you just like scaling up. It's like which would be more promising in your mind?
So for me, I generally will try to make sure that the motion data that we start with is fairly clean. I mean, it's like any other machine learning system, garbage in, garbage out. So if there's a lot of artifacts in your motion data, then your controller could very well start learning some unnatural behaviors, like maybe a lot of jittering or sliding.
Yeah, but the argument would be after I train like the generator and I frozen that, my low-level controller can always like correct those like invisible command. For example, like you just give a garbage like reference motion, but my policy because training RL for a long time, so it can correct by itself.
Well, you can correct some of the artifacts to some degrees. Well, because if you have some unnatural artifacts in your generated motions, your simulated controller can still try to reproduce artifacts. Like it can try to jitter some of its joints very quickly if that's what the reference motion is telling it to do.
Yeah. Okay.
Yeah.
Yeah, thanks. I also have the same concerns, but yeah, I just want to hear people like you. What's your opinion? Yeah.
Mhm. Yeah, I think it doesn't hurt to do some curation to make sure the data set is relatively clean.
Yeah, I had a question. So when your controller is combining different behaviors, like in the like walking and punching example,
Mhm.
how sensitive are the hyperparameters of the discriminator? Like, did you try larger or smaller models or try different sequence lengths, and how did that affect the like behavior stitching?
Right. Yeah. So in general, these adversarial setups, they can be fairly finicky. So you do have to tune the hyperparameters carefully with these particular methods. So for the discriminator, we do have to do a fair bit of hyperparameter tuning to get things to work. But I think once you find a good set of hyperparameters, so if for all these tasks we use exactly the same set of hyperparameters for all these different tasks, and they seem to work relatively well. So I think the challenge is finding that initial set of good parameters that you can use for your experiments.
Okay.
No, but I think like the same can be said for any machine learning problem, right? You have to figure out the right network structure, figure out the right learning rates and hyperparameters. So I think this is fairly in line with that workflow.
And I'm assuming the discriminator does like work over sequences, right?
Yep. The discriminator gets to look at 10 frames in
10.
this particular example.
Hi, Jason. Thanks for the great talk. I also have one question. It's a little bit high level. And I just observed that the input of the public control policy always includes the current state and the target state, right? So it naturally assumes the policy is a low-level tracking policy. And also it naturally assumes we need a hierarchical architecture. That means we need a motion planner, right?
Okay. So for clarification, not all of the results that I show are tracking controllers. So the controller is trained using adversarial imitation learning. It's not a tracking controller. It doesn't receive target states as input.
Oh, I see.
Yeah.
So,
but the results that I show later for some of the terrain traversal work, that was a tracking controller.
Yeah. So I'm wondering what's your opinion about developing end-to-end policy, like for many behaviors in our human behaviors, we do it subconsciously, right? Just take one very concrete example. How can we learn like some behaviors like when we tend to fall down, we take a step, for example, the left leg, take a step and prevent us from falling back. So how can we learn such behavior from just from motion imitation, or how can we really go beyond motion tracking? Like your title.
Oh yeah, so my preference generally is to do things end to end. I think a lot of people they use this motion plan and low-level tracker hierarchy at the moment because that's the easiest thing to do. It's easier to train these modules separately than to try to train them end to end. But so from my side, I would generally prefer to train this model end to end whenever possible, and that's something that we are working on.
Okay.
And one way to train these models end to end and not have to rely on motion tracker would be to use something like adversarial imitation learning, where you're not limited to just strictly tracking a given reference motion. And latent variable models would be another example of that.
Thank you.
Yeah, I have one more question. Will you use like some technique as like adaptive sampling to change like the distribution of your data? Because for example, like your data source have so many like walking and some more challenging like jump or like crouching down, and you just have like say 2% of data related to crouching, but now your policy can success like 100% for walking, but 6% for crouching. Then what you will do?
Yeah, I think data reweighting is pretty much standard practice for most of the frameworks nowadays. So whenever you try to train on larger data set, you have to do some rebalancing of your data. And for us, whenever we scale to a large motion data set, we do apply adaptive sampling to reweight the data depending on the performance of the controller on the different motion clips.
Okay.
Yeah, so I think that's kind of standard practice now.
Okay, cool.
Yeah.
And looking forward, like if in the future, like we don't consider like a single robot itself, we also consider like your interact with other object.
Yep.
Do you think something will change to your pipeline, or it always be a generator and a physics-based like policy, and then those two modules are looping together?
Oh, yeah. So moving forward, we probably won't have a motion generator and a physics-based tracker. It would just be an end-to-end model, remove this dependency on the motion generator and the motion planner. And in terms of object interactions, so I think as long as you have the motion data, the motion imitation techniques that we use will probably be similar. The big thing that will probably change will be in terms of perception. So how do you represent the state of the objects, the environments around the character? Most of the controllers that we have now, they rely primarily on proprioception. But I imagine for more complex object interaction tasks, you do have to incorporate more vision and perception into the model. But otherwise, I think the training strategy of imitating reference motions will probably stay relatively similar.
Okay.
Yeah, I mean, at the end of the day, motion tracking is kind of the motion control equivalent of supervised learning, and I don't think that's going away anytime soon in machine learning.
But do you consider like a generator that always that also generate like the future state of the object?
Oh, yeah, I think that'll be reasonable. So if you want to rely on a motion planner, then your motion planner will probably have to predict the state of the future state of the environment as well, in addition to the character.
Okay, then the generator will somehow like inherently become like physical aware, or at least like
Well, it will be physics aware up to what it can observe in the motion data set. So some of the behaviors in simulation will probably be quite different from data. So I don't think a motion planner that's trained strictly on kinematic motion data will be as physics aware as, let's say, a physics-based controller that is interacting with a simulated environment.
But it's just like extending like your Packer work. Would that be a way to like somehow drag like the generator to more physical aware?
Oh, yeah. So if you train the motion generator using data from the physics simulation, yeah, that will probably make the motion generator more physics aware.
Okay, thanks.
I have a question. So I want to ask how specialized these policies are when it comes to the data you're using for the motions you're using for training them. I think this is related to the previous question where you mentioned that there is some reweighting going on. Do you need to select specific motions from a mass, or can you train a policy like that on potentially all the data from
Right. Yeah, so again, it depends. It varies from project to project. So for this particular policy, we curated a data set of various locomotion skills. I think this wasn't even from AMAS, it was from the SFU data set. But for some other projects, like trying to train a general tracker on the G1, we do try to scale up to all of AMAS as well. So kind of the amount of motion data we use depends on I guess, the goals of a particular project.
I see, that makes sense. And one more question. I noticed that you are using like these motion generator systems to actually generate more motions for training. I was wondering, what are your thoughts when it comes to using motions that are reconstructed from video? And you have some examples like that in this tennis paper, in the skills from video paper as well. How plausible would be that path? I understand that potentially with the level of curation you want, that might be an obstacle. Like there might be too much noise in this in these motions generated from videos. But just wanted to hear your thoughts on this.
Yeah, so I think when reconstructing motion data from videos is a very promising direction. Yeah, and we have a few papers that tries to do exactly that. And I think the main challenge that we've always ran into is one, the quality of the motions from these vision-based post-estimation models are still pretty far from the quality we get from mocap. They tend to contain a lot of artifacts. The other problem is that the estimation of the global motion tends to be not very reliable. And the third is that for a lot of the motions that you reconstruct from real-world videos, humans are never walking in a completely flat, empty environment. There's always some other objects and kind of irregularities in the environment. And simply reconstructing the motion without reconstructing the environment often makes that motion unusable because your character might be walking in the middle of the air. The motion might be walking in the middle of the air, and you have no idea what the character is stepping on or what the character is interacting with. So because of those challenges, we still find it difficult to really scale up imitation from video data beyond just maybe more task-specific domains. But again, there's a lot of work that's been done in computer vision to improve these motion reconstruction and scene reconstruction methods. And I guess video mimic is one example to show maybe what you can do with current state-of-the-art methods. And I think as those vision-based techniques do improve, eventually video will become a very valuable source of motion data. I think we're just maybe not quite there yet, but it's probably just a matter of time.
Yeah, and one last question: how challenging is it to use? I understand that you are using like humanoid specific dimensions and proportions for the body. How challenging is to actually handle humanoids of different proportions, different heights, or different,
for the most part. Yeah, for the most part, it's not that challenging. There has been quite a bit of existing work that tries to train general controllers on characters with different morphologies, and they seem to work fairly well. It's just a matter of scaling up training. You can think of morphology randomization as just like another kind of domain randomization that you apply for sim-to-real transfer. So I think that should be fairly doable for the most part.
Okay.
Yeah. No, well, in fact, it has already been done. So yeah.
Great. Thank you very much. Thank you very much for the great talk.
Do people online still have more questions? If not, thank you very much, Jason, for devoting time for the great talk and the extended Q&A session. And we're looking forward to seeing you in the future. Thank you very much.
Yep, thanks for the invite.